Pluto has always been the rebel of our solar system, distant, defiant, and shrouded in secrets. Once known as the ninth planet, its controversial reclassification in 2006 sparked debates that still rage today. But whether you call it a planet or a dwarf planet, one thing is undeniable. Pluto is a world of breathtaking enigmas, a frozen outpost at the edge of our cosmic neighborhood that refuses to give up its mysteries easily. Imagine a place where the sky is perpetually twilight, where nitrogen glaciers crawl across the surface, and where heart-shaped plains of frozen carbon monoxide stretch for miles. This isn't science fiction, it's the bizarre reality of Pluto, a world so strange it feels almost otherworldly. What makes Pluto so endlessly fascinating isn't just its icy, rugged landscape or its lonely orbit billions of miles from the Sun. It's the sheer number of unanswered questions that linger even after humanity's most advanced spacecraft, New Horizons, gave us our first close-up look in 2015. Why does Pluto glow with an eerie, hazy atmosphere when it's so far from the Sun's warmth? What lurks beneath its frozen crust? Could there be hidden oceans defying the extreme cold? And why do some of its moons behave in ways that defy the laws of gravity as we understand them? These aren't just scientific curiosities, they're cosmic riddles that could rewrite what we know about the outer reaches of our solar system. Today, we're embarking on a journey to uncover 25 of Pluto's most baffling mysteries, each one more intriguing than the last. From unexplained geological formations that shouldn't exist to whispers of possible cryovolcanoes spewing ice instead of lava, every discovery about Pluto feels like peeling back another layer of an infinite cosmic onion. Whether you're a lifelong space enthusiast or just someone who loves a good unsolved puzzle, this exploration will leave you questioning everything you thought you knew about our solar system's most enigmatic world. So buckle up, we're about to dive deep into the unknown, where every answer only leads to more questions, and where Pluto's secrets might just hold the key to understanding the very edges of our celestial backyard. Pluto's most iconic feature, a massive heart-shaped plain named Tombaugh Regio after the planet's discoverer Tombaugh, is as puzzling as it is beautiful. Stretching over 1,000 miles wide, this bright, almost perfectly symmetrical formation is one of the first things New Horizons revealed when it flew by in 2015, and it immediately challenged everything scientists thought they knew about Pluto's geology. At first glance, the heart's left lobe, Sputnik Planitia, appears smooth and unblemished like a vast sheet of frozen nitrogen, but the closer researchers looked, the stranger it became. This isn't just a frozen plain, it's a dynamic, ever-changing landscape with bizarre polygonal structures and mysterious convection cells churning just beneath the surface, as if the ground itself is breathing. What makes Tombaugh Regio so baffling isn't just its shape. The entire region sits 3.5 kilometers lower than the surrounding terrain, as if something massive, maybe an ancient impact, dug out a colossal basin that later filled with volatile ices like nitrogen, carbon monoxide, and methane. But here's the twist, the heart's position isn't random. It's aligned almost perfectly opposite Pluto's largest moon, Charon, as if locked in place by some unseen gravitational dance. Some scientists think this isn't a coincidence, that the weight of Sputnik Planitia's ice might have actually tipped Pluto over time, reorienting the entire dwarf planet to keep this region fixed in its current spot. Even stranger, New Horizons detected no impact crater beneath the heart, leaving its origins a total enigma. If it wasn't carved by a collision, how did it form? Could there be hidden forces beneath Pluto's crust, perhaps pockets of slushy, semi-liquid nitrogen reshaping the surface in ways we've never seen before? And why does the boundary between the heart's bright lobes and Pluto's darker terrain look so unnaturally sharp? Every answer we think we have just leads to more questions, proving that even in the frozen reaches of our solar system, nature still has surprises up its sleeve. Pluto's nitrogen glaciers are nothing short of a geological paradox, rivers of ice that defy every rule we've learned from studying Earth's frozen landscapes. Unlike the slow, steady creep of terrestrial glaciers, Pluto's version moves in unpredictable bursts, carving valleys and reshaping plains in ways that leave scientists scratching their heads. These aren't just sheets of frozen nitrogen. They're dynamic, almost alive, flowing across the dwarf planet's surface like honey poured over uneven terrain, except honey doesn't suddenly speed up, split into fractal patterns, or vanish into nowhere. The stark contrast to Earth's glaciers becomes even more bizarre when you consider the forces at play. On our planet, gravity and temperature shifts drive glacial movement, but Pluto's weak gravity, just 6% of Earth's, should make such rapid, large-scale flows nearly impossible. Yet New Horizons captured sprawling glacial lobes extending hundreds of miles, some even spilling into crater rims like frozen waterfalls. Even stranger, these glaciers appear to be fed by a process called sublimation, where nitrogen ice vaporizes from one region and refreezes in another, creating a bizarre cycle of evaporation and deposition that shouldn't sustain such dramatic erosion. What really baffles researchers is the uneven distribution of these icy flows. Some regions, like the western edge of Sputnik Planitia, show glaciers crawling at a snail's pace, while others exhibit frantic, almost chaotic movement. One theory suggests hidden heat sources beneath Pluto's crust, perhaps residual warmth from radioactive decay or even tidal friction from Charon, could be softening the nitrogen ice, turning it into a slushy, mobile mass. Others speculate that the peculiar mix of methane and carbon monoxide ices intermixed with nitrogen might lower its melting point, allowing it to flow under conditions that would keep water ice locked in place. Then there's the mystery of the disappearing glaciers. Certain areas show evidence of ancient nitrogen flows that have simply stopped. Did Pluto's climate shift dramatically over millennia, freezing these rivers in their tracks? Or is there some unseen threshold, a tipping point in temperature or pressure that suddenly turns these glaciers on or off like a cosmic switch? Every image from New Horizons seems to add another layer of intrigue, proving that even in the coldest corners of the solar system, nature finds ways to keep us guessing. The implications stretch far beyond Pluto. If nitrogen glaciers can behave this erratically in such an extreme environment, what does that mean for our understanding of ice dynamics on other distant worlds? Could similar processes be at work on Kuiper belt objects like Eris or Makemake? For now, Pluto's capricious ice remains one of its most tantalizing puzzles, a reminder that even the most familiar geological phenomena can take on alien forms when viewed through the lens of an icy world 4 billion miles from home. Rising from Pluto's shadowed eastern hemisphere like a nightmare of frozen blades, the Tartarus dorsal region defies every expectation of how ice should behave. These aren't mere hills or cracks, they're jagged methane ridges, some soaring taller than New York City skyscrapers. Their knife-edge peaks spaced so evenly it looks as if some cosmic giant raked claws across the dwarf planet's surface. When New Horizons beamed back the first images, scientists gasped. Nothing in our solar system prepares you for this. A labyrinth of icy spires stretching hundreds of miles, their sides so steep and polished they reflect sunlight like mirrors. How could such extreme formations exist in a world with virtually no atmosphere? On Earth, wind and water carve dramatic landscapes over eons, but Pluto's thin air, about 100,000 times less dense than ours, shouldn't have the strength to lift a feather, let alone sculpt mountain-sized shards of ice. Yet here they stand, their razor-thin edges untouched by time. Some researchers argue sublimation, the direct transformation of ice to gas, could be the artist here. Imagine methane ice evaporating unevenly, leaving behind towering spines where tougher material resisted the process. But there's a problem. Sublimation typically creates chaotic, pitted surfaces, not these unnaturally uniform blades. Another theory suggests seasonal temperature swings might be to blame. Pluto's elliptical orbit brings it closer to the Sun for decades at a time, potentially warming methane deposits just enough to make them expand and contract. Over millions of years, this thermal stress could fracture the ice into these bizarre formations, but critics point out that similar cycles occur elsewhere in the solar system without producing anything remotely like Tartarus Dorsa. The ridge's precise alignment also hints at something stranger, perhaps ancient tidal forces from Charon stretching Pluto's crust like taffy, or even residual heat from radioactive elements below the surface creating convection currents in the ice. Then there's the wild card, wind erosion. Even Pluto's whisper-thin atmosphere might pack surprises. During periods of heightened solar activity, gases could temporarily thicken, allowing light breezes to carry microscopic ice particles that sandblast the terrain over astronomical timescales. It's a long shot, but New Horizons did detect faint streaks near the ridges that look suspiciously like wind-blown deposits. What makes Tartarus Dorsa truly unsettling is how little we understand about its life cycle. Are these blades actively growing, or are they frozen relics of a more violent epoch? Could they be collapsing under their own weight too slowly for us to notice? Every proposed explanation feels like trying to solve a jigsaw puzzle with half the pieces missing, and the ones we have don't fit together. One thing's certain, this alien landscape proves that even in the realm of ice, nature has tools in its workshop we've yet to imagine. Pluto's atmosphere shouldn't exist, at least not like this. 4 billion miles from the Sun, where temperatures hover near -400 degrees Fahrenheit, scientists expected little more than a wispy, transient gas layer clinging feebly to the dwarf planet. But when New Horizons glanced back at Pluto's silhouette during its 2015 flyby, it captured something astonishing. A towering, multi-layered haze stretching 100 miles high, glowing blue against the inky blackness of space. This wasn't just a thin veil, it was a complex, structured shroud, with dozens of distinct layers stacked like ghostly pancakes, each one whispering secrets about Pluto's alien weather. What makes these haze layers so baffling is their stubborn persistence. On airless worlds, solar radiation and tiny meteorites should blast away loose molecules within years, yet Pluto's haze has endured for millennia. Even stranger, the layers aren't static. They rise and fall like an invisible ladder, with some strata drifting higher during the dwarf planet's long, slow summers when sunlight weakly warms the surface. The leading theory points to methane as the culprit, not as a simple gas, but as the starting ingredient for a cosmic chemistry experiment. When ultraviolet light from the distant Sun hits methane in Pluto's upper atmosphere, it triggers a cascade of reactions, transforming simple molecules into complex hydrocarbons like ethylene and acetylene. These heavier compounds clump together into tiny particles, forming the haze. But here's the twist: instead of falling straight down, they're caught in an atmospheric dance, buoyed by weak updrafts and shaped by winds we can barely detect. The real shock came when New Horizons analyzed the haze color. Most planetary hazes scatter sunlight into soft blues or whites, but Pluto's layers contain organic compounds called tholin sticky, tar-like molecules that rain down to give the surface its reddish hue. These aren't just byproducts, they're evidence of an active carbon cycle happening in near-total darkness. Some researchers speculate the haze might even act like a slow-motion greenhouse, trapping just enough heat to maintain subsurface oceans or fuel those mysterious nitrogen glaciers. Yet for every answer, the haze poses two more questions. Why do the layers form such precise bands instead of blending together? Could there be unseen topography, mountains or basins altering air currents to create these patterns? And most perplexing of all, how does a world with atmospheric pressure 100,000 times weaker than Earth sustain such intricate structure? Every layer seems to taunt us, a reminder that Pluto, even in its frozen solitude, plays by rules we're only beginning to decipher. Pluto's polar regions hold one of its most visually striking mysteries, caps not of white ice, but of deep reddish-brown stains that look like spilled paint across the dwarf planet's frozen canvas. These strange markings, concentrated sharply at both poles, aren't random discolorations. They're likely tholins, the same complex organic molecules that tint Pluto's haze layers and paint its surface in rusty hues. But here's what defies logic. If tholins form everywhere sunlight touches methane in Pluto's atmosphere, why do they pile up so dramatically at the poles, leaving other regions comparatively pale? The answer might lie in Pluto's extreme seasons, which last for decades at a time. During its long winter, a pole plunges into continuous darkness for over 100 Earth years, allowing frigid temperatures to condense atmospheric gases like methane and nitrogen onto the surface as frost. When sunlight finally returns, it triggers a photochemical frenzy. Ultraviolet radiation breaks apart methane molecules, which then recombine into heavier hydrocarbons. Over centuries, these compounds grow more complex, eventually forming tholins that rain down as ruddy snow. But this process alone doesn't explain the stark polar concentration. New Horizons revealed another clue. The poles are littered with pits and cracks, some hundreds of meters deep. These features might act as cold traps, capturing and concentrating tholins while smoother equatorial regions let them blow away. There's also the possibility of uneven methane distribution. Imagine Pluto's poles as sponges, soaking up more atmospheric gases than the rest of the surface during their endless winters. When the thaw comes, these areas would have a head start in tholin production. The wild card, Pluto's wobbly orbit. Its elliptical path around the Sun creates lopsided seasons, with northern and southern hemispheres experiencing different intensities of sunlight over millennia. This could explain why one polar cap appears darker and more extensive than the other, a record of ancient climate shifts frozen in time. Even more perplexing is the way these reddish stains abruptly stop at certain latitudes, as if some invisible barrier prevents their spread. Could subsurface geology or hidden wind patterns play a role? Every theory leads to new questions, proving that Pluto's rusty poles are far more than just a colorful curiosity. They're a dynamic puzzle written in chemistry and ice. Deep in Pluto's frozen badlands, two massive mountains stand as silent sentinels, Right Mons and Pickard Mons, potential cryovolcanoes that defy everything we know about volcanic activity. Unlike Earth's fiery peaks that spew molten rock, these behemoths may erupt with a slow-motion fury of slushy ice, ammonia, and methane, painting the landscape with frozen eruptions that could rewrite the rules of planetary geology. Towering over 2.5 miles high with sprawling bases stretching 100 miles wide, their peculiar shapes, giant domes with central depressions, look eerily similar to shield volcanoes on Earth. But with a chilling twist, their plumbing might run on exotic ices instead of magma. The discovery sent shockwaves through the scientific community. New Horizons captured Right Mons' bizarre texture, its sides ribbed with concentric ridges like a frozen whirlpool, its summit sinking into a gaping pit nearly 30 miles across. Nearby, Pickard Mons shows similar scars, its flanks streaked with what appear to be ancient flow channels. If these are truly cryovolcanoes, their eruptions wouldn't be explosive bursts but sluggish oozes, with mixtures of water, ammonia, and nitrogen creeping across the surface like cold syrup before freezing solid. But the real mystery lies in their energy source. On active moons like Enceladus or Europa, tidal forces from giant planets flex their cores, generating enough heat to maintain subsurface oceans and power eruptions. Pluto, with its tiny moon Charon and no nearby gas giant, shouldn't have this luxury, yet here these icy giants loom, begging the question, what's melting Pluto's insides? Some scientists point to radioactive decay in Pluto's rocky core as a possible furnace, slowly leaching warmth upward over billions of years. Others speculate that antifreeze compounds like ammonia could lower the melting point of subsurface ices, creating pockets of slushy brine that occasionally breach the surface. The most tantalizing theory, these cryovolcanoes might not be extinct. While no active plumes were spotted during New Horizons' brief flyby, subtle color variations on their flanks hint at possible recent activity. Imagine a volcanic eruption where the lava never gets warmer than -300 degrees, creeping forth in a silent, glacial spectacle unseen anywhere else in the solar system. The implications are staggering. If Wright and Pickard Mons are still functional, they could be delivering fresh ices and organic molecules to Pluto's surface, ingredients for probiotic chemistry that might lurk in hidden subsurface oceans. Even if dormant, their existence proves that geologic fire can burn in the coldest places, fueled by mechanisms we've only begun to decipher. Every ridge and fracture tells a story we're just learning to read, one where Pluto, against all odds, remains a world of hidden heat and slow, frozen fire. Pluto's surface tells a story that shouldn't exist, a tale of cosmic renewal written in ice. For a small, frozen world in the Kuiper belt, Pluto should be pockmarked with craters, its face scarred by billions of years of asteroid impacts like its distant neighbors. But when New Horizons mapped its terrain, scientists were stunned to find vast stretches of startlingly smooth plains, particularly in regions like Sputnik Planitia, where the landscape looks almost polished. This absence of craters isn't just unusual, it's a glaring contradiction for a body that's been around since the birth of the solar system. If Pluto has been geologically dead for ages, why doesn't it wear the same battered mask as other cold, distant worlds? The answer may lie in Pluto's hidden vitality. Unlike most Kuiper belt objects, which are static relics frozen in time, Pluto's surface appears to be resurfacing itself, erasing ancient impacts through processes we're only beginning to understand. The most compelling clue comes from those nitrogen glaciers, rivers of ice that could be slowly but steadily smoothing the terrain, filling in craters like a cosmic Zamboni. But glaciers alone can't account for all the missing scars. Some regions show such sparse cratering that scientists estimate their surfaces might be less than 10 million years old, a blink of an eye in geological terms. This points to something far more dramatic: cryovolcanism, tectonic shifts, or even the slow churn of convection cells beneath Pluto's icy shell, recycling its surface over and over again. What's truly baffling is the energy source driving this activity. Pluto is tiny, with a diameter barely half that of Earth's moon, and it orbits so far from the sun that solar heating is negligible. Yet somehow, it's holding onto enough internal heat to reshape its exterior. One theory suggests radioactive decay in Pluto's rocky core could be providing a weak but persistent heat source, while another posits that the dwarf planet's unusual axial tilt, tipped over nearly 120 degrees, creates erratic climate cycles powerful enough to redistribute volatile ices and erase old scars. There's even speculation that gravitational interactions with Charon might generate tidal friction, flexing Pluto's interior like warm putty and keeping its icy shell mobile. The implications are staggering. If Pluto, small, cold, and distant, can maintain geologic activity, what does that mean for other Kuiper belt objects? Could Eris, Makemake, or Haumea also be hiding dynamic interiors beneath their frozen surfaces? And if these worlds are more than inert fossils, what untapped forces are at play in the far reaches of our solar system? Pluto's smooth countenance isn't just a quirk, it's a challenge to our understanding of how planetary bodies age, evolve, and sometimes, against all odds, refuse to fade into quiet obscurity. Even more puzzling is the patchy distribution of these smooth terrains. Some areas, like the dark highlands of Cthulhu Macula, are heavily cratered, suggesting they've escaped the resurfacing that refreshed other regions. This selective erasure hints at an even deeper mystery. localized hotspots or subsurface anomalies that focus geologic activity in certain zones while leaving others untouched. Could Pluto's core be asymmetrical, with heat concentrated in specific areas? Or are volatile ices like nitrogen pooling in some basins and not others, creating a planetary-scale game of freeze and thaw? Every unanswered question about Pluto's youthful terrain pulls us deeper into a paradox. How can a world so small and so cold keep rewriting its own history, erasing the evidence of time itself? It's as if Pluto refuses to play by the rules, defying expectations, whispering secrets, and forcing us to reconsider what's possible at the frozen edge of our cosmic neighborhood. Pluto's Sputnik Planitia holds one of the solar system's most surreal spectacles, a vast glacial plain where entire mountains drift like icebergs in a frozen sea. These aren't stationary landforms but free-floating hills, some spanning several miles across, slowly jostling and colliding in a slow-motion ballet across the nitrogen ice. New Horizons captured their bizarre dance in stunning detail. Jagged fragments of water ice, denser than the surrounding nitrogen, bobbing like corks in a cosmic slush, occasionally fracturing and merging in ways that defy every textbook on planetary geology. What makes these floating hills so mesmerizing isn't just their motion, it's the sheer improbability of their existence. On Earth, icebergs float because liquid water is denser than solid ice, but Pluto's scenario flips this logic upside down. Here, water ice acts as the rock, while softer nitrogen ice behaves like a fluid over geologic time, allowing these massive chunks to glide and spin with eerie grace. Some hills cluster into chains, like broken pieces of a puzzle trying to reconnect, while others stand alone, their sharp edges suggesting recent collisions or splits. The most mind-bending detail, many of these hills are polygonal, as if shaped by an unseen force into geometric perfection. Scientists suspect convection currents beneath Sputnik Planitia may be the hidden choreographer. As nitrogen ice warms slightly from below, it rises in plumes, dragging the floating hills along invisible conveyor belts. When these currents cool and sink, the hills drift apart, only to be herded together again by another rising cell. It's a process that should take millennia, yet New Horizons spotted evidence of recent fractures and rearrangements, hinting that this dance is far more dynamic than anyone predicted. Then there's the mystery of the cellular terrain surrounding the hills, a honeycomb pattern of pits and ridges where nitrogen ice sublimates and refreezes in cycles. Some researchers believe these patterns create pressure zones that nudge the hills into alignment, like debris caught in eddies of a stream. Others propose that sunlight, weak as it is, heats darker water ice hills unevenly, causing localized sublimation that propels them unpredictably. The implications ripple beyond Pluto. If nitrogen plains can host such mobile geology, what might lurk on similar worlds like Triton or Eris? Could these hills be time capsules, preserving ancient ices untouched for eons while the surface renews itself around them? For now, their silent drift remains one of Pluto's most hypnotic enigmas, a reminder that even in the stillness of space, the ground beneath our feet or spacecraft might not be as solid as it seems. Pluto's atmosphere behaves like a cosmic yo-yo, expanding and collapsing in ways that leave scientists utterly perplexed. Since the 1980s, when astronomers first began measuring its atmospheric pressure, they've documented swings so dramatic they defy all expectations, sometimes doubling or even tripling in density before plummeting again. For a world where surface temperatures average minus 380 degrees Fahrenheit, such volatility is like watching an ice cube spontaneously boil, then refreeze in deep space. The first shock came in 1988, when observations during a stellar occultation where Pluto passed in front of a distant star revealed an atmosphere far thicker than models predicted. Over the next 3 decades, follow-up measurements showed wild fluctuations, peaking around 2015 when New Horizons flew by. That's when the plot thickened. Instead of confirming a steady atmospheric rise as Pluto moved closer to the Sun, the spacecraft found signs the pressure had already started dropping despite being years away from the dwarf planet's maximum solar exposure. This bizarre timing mismatch suggests Pluto's atmosphere doesn't follow simple seasonal rules. Two leading theories attempt to explain this roller coaster. The first points to volatile ices, mainly nitrogen, sublimating from Pluto's surface as sunlight intensifies during its 248-year orbit. Imagine Sputnik Planitia, that massive heart-shaped glacier acting as a planetary scale pressure valve. When solar warmth creeps in, nitrogen ice vaporizes into gas, ballooning the atmosphere. As Pluto swings back toward the frigid outer solar system, the gas refreezes, causing the atmosphere to collapse like a deflating balloon. But here's the catch: this process should lag behind Pluto's seasons by decades, not precede them. The second theory involves Pluto's bizarre axial tilt, a staggering 120 degrees, creating lopsided climate extremes. Unlike Earth's relatively gentle seasons, Pluto practically rolls around the Sun like a barrel, alternately roasting and freezing entire hemispheres for centuries at a time. This could trigger runaway feedback loops, darker tholin-stained regions absorbing extra heat, accelerating ice loss in unexpected ways. Some researchers speculate that Pluto's poles might flip roles, with one cap suddenly releasing stored gases while the other freezes solid. Yet even these explanations falter when faced with the sheer speed of changes. In 2019, just 4 years after New Horizons' visit, fresh occultation data revealed the atmosphere had shrunk by over 20%, a change that should have taken 50 years based on conventional models. Could hidden reservoirs of nitrogen lurk beneath Pluto's crust, erupting unpredictably like underground geysers? Or does its haze, those mysterious layered particles, act as a thermal blanket, trapping or releasing heat in chaotic cycles? The stakes are higher than just solving a Pluto puzzle. If such a small, cold world can experience atmospheric convulsions this severe, what does that mean for exoplanets on the fringes of other star systems? Could their climates swing even more violently, rewriting our definitions of habitable zones? Every new observation peels back another layer of mystery, proving that Pluto's atmosphere, much like the dwarf planet itself, refuses to be boxed into our terrestrial expectations. One thing's certain, this isn't just a dying gasp of a frozen world. It's the erratic heartbeat of a surprisingly dynamic one, cutting across Pluto's darkened highlands like scars from some cosmic whip. The enigmatic dark streaks of Cthulhu macula present one of the dwarf planet's most visually arresting riddles. Stretching for hundreds of miles, these parallel markings, some as wide as skyscrapers, are tall, align with eerie precision, as if drawn by an invisible hand. When New Horizons first revealed them in 2015, scientists immediately noticed something uncanny: their uniformity. Unlike chaotic impact craters or haphazard geological fractures, these streaks follow a consistent northeast-southwest orientation, almost as if responding to some hidden directional force. The most striking theory points to wind. Despite Pluto's wispy atmosphere, 100,000 times thinner than Earth, researchers now suspect periodic surges in atmospheric pressure might create fleeting breezes strong enough to move fine particles. Imagine methane or nitrogen frost delicately deposited across Cthulhu macula's ancient water ice bedrock, getting nudged by gentle gusts over millennia. The streak's alignment could then reflect global wind patterns shaped by Pluto's extreme axial tilt, with gases rushing from warmer equatorial zones toward colder polar regions. But there's a catch: these winds would be barely perceptible, moving at perhaps a few miles per hour at most. Could such feather-light forces really carve persistent features across a frozen landscape? Alternative explanations delve into cryovolcanic leftovers. The region borders Pluto's icy mountains, where potential cryovolcanoes like Right Mons may have once oozed sludgy mixtures of water ice and dark organic compounds. If these eruptions occurred during periods of atmospheric thickening, volatile materials could have been strewn across the surface in linear patterns before freezing in place. Spectral analysis adds weight to this idea. The streaks reflect less sunlight than their surroundings, hinting at tholin-rich compositions similar to other areas where complex hydrocarbons coat the ice. Yet another hypothesis suggests these streaks might be ancient tidal imprints from Charon. When Pluto and its largest moon first settled into their locked orbital dance billions of years ago, gravitational stretching could have fractured the brittle crust, creating weak zones later filled by wind-blown deposits or cryovolcanic seepage. This would explain why the markings appear primarily in Pluto's oldest terrains, preserved like fossils in the ice. The true marvel lies in their persistence. Unlike the shifting glaciers of Sputnik Planitia, these streaks have remained frozen in time literally. Their crisp edges and lack of overlying craters suggest they've avoided significant erosion or resurfacing, making them potential time capsules from an era when Pluto's atmosphere was far more dynamic. What secrets do they hold about the dwarf planet's climate history? Could they be recording ancient wind directions like cosmic weather vanes, or marking the paths of long-vanished ice rivers? For now, they stand as silent witnesses to forces we've only begun to comprehend, a reminder that even in stillness, Pluto's surface speaks volumes about its turbulent past. Pluto's moon system looks less like an orderly family and more like a celestial mosh pit where Charon, Styx, Nix, Kerberos, and Hydra whirl around their host in a chaotic ballet that defies every rule of orbital mechanics. These aren't neat, predictable circles or gentle ellipses like the moons of Mars or Earth. Instead, they're locked in a gravitational free-for-all, tumbling and swaying with such erratic energy that scientists still struggle to explain how the whole system hasn't collapsed into chaos. At the center of this cosmic dance is Charon, Pluto's largest moon, so massive relative to its host that the two actually orbit a shared point in space, making them the solar system's only known binary dwarf planet system. This gravitational tug-of-war sets the stage for the madness that follows. While Charon and Pluto remain locked in their intimate embrace, the other four moons, tiny, irregularly shaped and far more distant, are subjected to a relentless gravitational squeeze. Nix and Hydra, the most visible of the smaller moons, wobble like spinning tops, their axes of rotation shifting unpredictably over time. Images from New Horizons revealed Nix sporting a bizarre, tumbling motion, its bright spots and dark patches appearing to migrate across its surface as if the moon itself can't decide which way is up. The real shock came when astronomers tried to model the moon's long-term stability. Standard orbital predictions suggest that systems like Pluto's should either settle into resonances, where moons orbit in neat integer ratios like Jupiter's Galilean moons, or spiral into collisions within a few million years. Yet Pluto's retinue has somehow avoided both fates for billions of years. Styx, Kerberos, and Hydra follow orbits that are inexplicably close to resonances with Charon but never quite lock in, creating a persistent state of near chaos. Some simulations suggest the smaller moons might even swap orbits periodically, as if playing musical chairs with gravity. What keeps this fragile balance from collapsing? One theory points to Pluto's complex gravitational field, shaped by the uneven distribution of mass across its surface, particularly the heart-shaped Sputnik Planitia, which may act as a hidden counterweight. Another possibility involves the Kozai mechanism, a gravitational quirk where the pull of Charon and the Sun could be nudging the smaller moons into ever-changing orbits. Then there's the wildcard collisions. The system might be a cosmic game of pinball, where occasional impacts between moonlets or passing Kuiper belt objects knock the moons just enough to prevent total destabilization. The implications stretch far beyond Pluto. If such a delicate arrangement can persist in this tiny corner of the solar system, what does that mean for exoplanet systems with similar configurations? Could there be binary worlds in distant star systems where moons pirouette in equally chaotic harmony? For now, Pluto's erratic lunar dance remains one of its most mesmerizing mysteries, a reminder that even in the cold reaches of space, gravity has a flair for the dramatic. Pluto's surface glows and fades like the screen of a cosmic monitor stuck on random bright regions reflecting up to 80% of sunlight, while nearby areas absorb nearly all of it, creating stark contrasts that baffle astronomers. This isn't just simple shading from topography, it's a patchwork quilt of reflectivity where adjacent terrains can differ as drastically as fresh snow and charcoal. The brightest zones, like the heart-shaped Tombaugh Regio, blaze with almost mirror-like intensity thanks to fresh nitrogen ice, while the darkest patches, such as the sprawling Cthulhu macula, swallow light like cosmic black holes, reflecting less than 10%. What makes these variations so perplexing isn't their existence, but their bizarre distribution. If volatile ices like nitrogen, methane, and carbon monoxide are constantly cycling through sublimation and deposition, why don't they spread evenly, smoothing out these extremes over time? New Horizons delivered a crucial clue. The bright and dark regions aren't randomly scattered. They cluster in ways that suggest hidden forces directing their placement. The western lobe of Tombaugh Regio, Sputnik Planitia, isn't just bright, it's unnaturally bright, as if someone polished it yesterday. Spectral data reveals this area is dominated by nitrogen ice so pure it acts like a frozen mirror. Meanwhile, just a few hundred miles east, the Viking Terror region shows bizarre intermediate tones, mottled terrains where methane seems to have seeped up from below, staining the surface like ink blots. The sharp boundaries between these zones imply something is actively segregating these ices, preventing them from mixing. One theory points to Pluto's weak gravity and exotic seasons. During its decades-long summers, sunlight barely strong enough to warm a winter glove can still cause nitrogen and methane ices to vaporize in sunlit areas. These gases then migrate to colder regions, often just over the horizon, where they refreeze, creating bright new deposits. But this doesn't fully explain why some areas stay dark. Cthulhu macula, for instance, appears to be coated in Tholen's complex organic gunk formed when methane gets cooked by solar radiation. Yet even here, there are bright streaks cutting through the darkness like graffiti from some celestial artist. Could underground reservoirs be venting fresh ice in localized bursts? Or do Pluto's winds faint as they herald these materials like a cosmic sorting machine? The plot thickens when you consider time. Pluto's axial tilt of 120 degrees creates seasons so extreme that over millennia, entire polar caps might evaporate and reform elsewhere on the globe. This could explain why some dark regions show faint, ghostly outlines of ancient bright zones beneath them, layers of history written in ice. But if this cycle has been ongoing for eons, why haven't the ices homogenized? The answer might lie in Pluto's heart. Sputnik Planitia's massive nitrogen glacier could act as a stabilizer, its sheer weight locking volatile materials in place while the rest of the surface undergoes constant renewal. The implications stretch beyond Pluto. Similar patchwork terrains appear on Neptune's moon Triton and other Kuiper belt objects, hinting that this isn't just a fluke, it's a fundamental property of icy worlds with trace atmospheres. Each bright and dark patch is a window into processes we've barely begun to understand: cryovolcanic resurfacing, hidden climate cycles, or even the slow segregation of ices by molecular weight. For now, Pluto's shimmering, shadowed face remains a cosmic roar, test one where every interpretation leads to deeper questions about how small, cold worlds wear their histories on their surfaces. Pluto's Tartarus Dorsa region hides one of the most visually unsettling landscapes ever photographed, a stretch of highlands covered in what can only be described as snakeskin. These eerie formations, captured in stunning detail by New Horizons, ripple across the terrain in intricate, overlapping scales, each one the size of a city block. The resemblance to reptilian hide is so uncanny that scientists initially questioned whether they were seeing some bizarre trick of light and shadow. But the closer they looked, the stranger it got. These ridges aren't just surface markings, they're three-dimensional structures, some towering hundreds of feet high, their edges razor-sharp despite billions of years of erosion. What makes this snakeskin terrain so baffling is its sheer improbability. On Earth, similar patterns sometimes emerge in mudflats or drying paint, where shrinking materials crack into polygonal networks. But Pluto's scales are far more complex, arranged in layered arcs, like armored plates stacked by some cosmic reptile. The leading theory points to sublimation, where volatile ices like methane slowly vaporize under weak sunlight, leaving behind tougher water ice in raised ridges. Over millennia, this process could carve the landscape into these bizarre formations, but there's a glaring flaw. Sublimation typically creates chaotic, fractured surfaces, not these unnaturally uniform scales. Another camp argues for tectonic origins. Pluto's crust, strained by the weight of Sputnik Planitia or the gravitational tug of Charon, might have fractured in a global pattern, like a frozen lake cracking under pressure. The snakeskin ridges could be the scars of these ancient stresses, amplified by seasonal expansion and contraction as temperatures fluctuate by a few degrees over centuries. Yet this doesn't explain why the patterns concentrate in specific areas, avoiding other regions entirely. The wild card, wind, even Pluto's whisper-thin atmosphere might play a role. During periods of heightened atmospheric pressure, gentle breezes could carry ice particles, sandblasting certain areas while leaving others untouched. Over eons, this selective erosion might sculpt the scales into their current form. Some researchers even speculate that electrostatic forces generated by sunlight striking methane ice could levitate fine dust, allowing it to settle in these eerie reptilian patterns. The most haunting possibility is that we're seeing multiple processes at once, a slow-motion ballet of sublimation, tectonics, and particle drift working in concert to create something no single force could achieve alone. If true, Pluto's snakeskin isn't just a geological oddity. It's a masterpiece of celestial chaos, a reminder that even in the silent reaches of the Kuiper belt, nature has a flair for the dramatic. Every ridge and valley whispers secrets about forces we've only begun to fathom, proving that Pluto's mysteries run skin deep, literally. Pluto's atmosphere performs a cosmic magic trick, shimmering with an otherworldly blue tint while the surface below glows rusty red, creating a color clash that defies simple explanation. This striking contrast, captured in New Horizons' haunting backlit images, reveals a world caught between two identities. An icy body wrapped in a haze that behaves more like something from a distant exoplanet. The blue hue comes from sunlight scattering off tiny particles in Pluto's upper atmosphere, a phenomenon similar to what paints Earth's skies blue, but with a twist. Here, the scattering isn't caused by nitrogen or oxygen molecules, but by soot-like hydrocarbon clusters called tholins, forged when methane and nitrogen gas break apart under the sun's weak ultraviolet light. What makes this haze so extraordinary is its layered structure, dozens of delicate bands stacked like a celestial wedding cake, each one filtering sunlight differently. While most icy moons and Kuiper belt objects either lack atmospheres entirely or sport uniform, colorless hazes, Pluto's version dances with complexity. The blue tint intensifies at higher altitudes where finer particles dominate, while deeper layers take on a reddish glow from larger tholin aggregates. This gradient creates an ethereal halo around Pluto during sunrise and sunset, a spectacle unseen anywhere else in our solar system. The real puzzle lies in the disconnect between the atmosphere and surface. The same tholins responsible for the blue haze eventually snow down, staining Pluto's terrain with ruddy patches like Cthulhu macula. Yet this process feels oddly selective. Why doesn't the entire surface turn uniformly red over time? The answer may lie in Pluto's bizarre climate cycles. During its decades-long winters, atmospheric gases freeze onto the surface as frost, temporarily pausing tholin production. When sunlight returns, the thawing ice releases fresh methane, restarting the photochemical factory that builds the haze anew. This stop-start cycle could explain why some regions remain starkly bright while others darken with organic deposits. Even stranger is the haze resilience. At Pluto's distance, temperatures are so cold that most gases should condense and vanish within years, yet these layers persist. Some scientists speculate that cryovolcanoes or geysers might be replenishing the atmosphere with fresh volatiles from below, while others point to slow but steady sublimation from Sputnik Planitia's nitrogen glaciers. Either way, the system maintains a delicate balance, one that transforms simple molecules into a masterpiece of light and color, proving that even in the solar system's outer darkness, beauty thrives in the unlikeliest forms. The implications ripple beyond Pluto. If such a tenuous atmosphere can sustain complex hazes, what might exist on similar worlds like Eris or Sedna? Could their skies also shimmer with hidden hues, waiting for a passing probe to reveal them? For now, Pluto's blue veil remains a reminder that nature's artistry knows no bounds, painting the void with strokes we've only begun to decode. Among Pluto's most striking features, the so-called whale emerges like a shadowy leviathan frozen in time, a vast, dark expanse stretching over 1,000 miles along the dwarf planet's equator. Officially named Cthulhu Macula after the fictional cosmic entity, this region's eerie, whale-like silhouette stands in stark contrast to the bright plains of Tombaugh Regio just to the north. While most of Pluto's surface dances with frosty reflectivity, the whale drinks in sunlight, absorbing nearly all of it with a darkness rivaling fresh asphalt. New Horizons' spectral analysis revealed why. This area is coated in thick layers of tholins, complex organic compounds formed when methane and nitrogen are bombarded by solar radiation over eons. But here's the mystery. Why is this organic graveyard so sharply confined, as if someone drew a border and forbade the darkness from spreading? The whale's geology deepens the intrigue. Unlike the youthful, crater-free plains of Sputnik Planitia, this region is ancient, its surface pockmarked with impacts that hint at an age stretching back billions of years. Yet despite its antiquity, the whale shows signs of subtle activity, fractures and ridges suggesting it hasn't been entirely frozen in time. Some of these cracks align with the edges of brighter neighboring terrains, almost as if tectonic forces are pushing the two regions apart. One theory posits that the whale's dark tholins might be insulating the ice beneath, trapping enough heat to create slow-motion tectonic shifts. Another possibility involves volatile ices creeping underneath, lubricating the crust like a layer of grease and allowing it to crack under stress from Pluto's odd axial tilt. What's most baffling is the whale's resistance to resurfacing. While other parts of Pluto undergo constant renewal through glacial flows and cryovolcanism, Cthulhu Macula remains stubbornly unchanged, a relic from a more violent era. Some scientists speculate that its dark coloring acts like a solar sponge, warming the surface just enough to prevent fresh frosts from settling. Others wonder if the region sits atop a cold trap, a depression so deep and shadowed that any volatile gases drifting by freeze in place, sealing the ancient terrain beneath an ever-thickening shell of organic sludge. Then there's the enigma of its borders, the transition between the whale's Inkai plains and the bright, nitrogen-rich heart of Pluto isn't gradual, it's razor-sharp, like a coastline carved by some long-vanished tide. Could hidden subsurface boundaries, fault lines, or variations in heat flow be keeping these materials segregated? Or does Pluto's thin atmosphere play traffic cop, steering fresh frosts away from the darkened terrain? Every answer only exposes deeper layers of mystery, proving that even in the realm of ice and shadow, Pluto refuses to surrender its secrets easily. The whale's darkness might hold clues to Pluto's deepest past. Its tholins are more than just stains, they're chemical time capsules, preserving the building blocks of probiotic chemistry that could mirror the early stages of life's ingredients on Earth. If similar processes occur on other Kuiper belt objects, the cosmos might be littered with these organic reservoirs, silent and frozen, waiting for the right conditions to awaken their hidden potential. For now, the whale remains a silent sentinel, a testament to the forces that shaped Pluto's wild, untamed face, and a reminder that even in the farthest reaches of our solar system, darkness can hold the most illuminating secrets. Pluto's surface ice doesn't just sit there. It vanishes and reappears in planetary scale cycles so rapid they'd make Earth's seasonal changes look sluggish by comparison. This bizarre sublimation dance, where ices transform directly from solid to gas without becoming liquid, plays out across the dwarf planet's frozen plains with a speed that defies logic. On a world where sunlight is 1,000 times weaker than Earth's and surface temperatures hover near absolute zero, scientists expected geological processes to unfold at a glacial pace, literally. Yet New Horizons revealed ices that behave more like restless phantoms, creeping across the landscape in decades rather than millennia. Take the heart-shaped Tombaugh Regio, where vast deposits of nitrogen ice seem to evaporate and reform like clockwork. During Pluto's long, slow summers, weak sunlight vaporizes nitrogen from bright plains, sending ghostly tendrils of gas into the atmosphere. These molecules then drift toward colder regions, sometimes just over the horizon, where they refreeze as fresh frost. The entire cycle can complete in as little as a few Earth years, leaving behind stark transitions between bright and dark terrain that look almost painted onto the surface. What's baffling isn't just the speed, but the precision. In some areas, the boundary between fresh frost and ancient, tholin-stained ice is razor-sharp, as if drawn by an invisible hand. The energy source driving this activity is a head-scratcher. With solar input barely enough to power a desk lamp, conventional models can't explain how Pluto's ices mobilize so aggressively. One clue lies in the exotic composition of these frozen deposits. Nitrogen ice, which dominates Pluto's volatile inventory, requires 8 times less heat to sublimate than water ice. Mixed with traces of methane and carbon monoxide, it forms a cocktail of ices that can transition between states at temperatures that would lock most other materials in permanent stasis. But even this doesn't fully account for the observed pace. Researchers now suspect hidden feedback loops might be turbocharging the process. As darker tholin-stained regions absorb slightly more sunlight, they warm just enough to accelerate nearby ice loss, creating patches that grow exponentially once started. Meanwhile, brighter frosts reflect sunlight, cooling their surroundings and preserving themselves like icy oases. This self-reinforcing mechanism could explain why Pluto's surface looks like a frozen chessboard of light and dark squares, each one locked in a slow-motion battle between sublimation and condensation. The most tantalizing evidence comes from decade-old Hubble observations compared with New Horizons data. Certain regions, like the eastern edge of Cthulhu Macula, show dramatic darkening between 2002 and 2015, changes that shouldn't be possible without geologic activity. Some scientists argue these shifts hint at buried reservoirs of volatile ices, bubbling up through cracks in the crust like a frozen Yellowstone. Others propose that Pluto's lopsided seasons, caused by its extreme axial tilt, create temporary pressure differentials powerful enough to shuffle ices across the surface in global conveyor belts. The implications stretch far beyond Pluto. If a small, cold world can rewrite its surface in real time, what does that mean for other Kuiper belt objects? Could Eris or Make also be hiding hyperactive ice cycles beneath their seemingly static exteriors? For now, Pluto's restless ices remain a masterclass in thermodynamic defiance, proof that even in the solar system's deepest freeze, change is the only constant. Pluto's Virgil Foci region hides a geological nightmare, a sprawling network of fractures radiating outward like the legs of some monstrous cosmic spider. These aren't ordinary cracks. They stretch for hundreds of miles, some as wide as football fields. They're razor-straight paths intersecting at unnatural angles. When New Horizons first captured this eerie formation, scientists immediately recognized something unprecedented. No other icy world in the solar system displays fractures quite like this. The spider, as it's nicknamed, doesn't just scar Pluto's surface. It seems to claw upward from beneath, as if something below is tearing the dwarf planet apart from the inside. The leading theory points to tectonics' violent shifts in Pluto's crust caused by the freezing and expansion of a hidden subsurface ocean. Imagine water beneath the ice turning to ice, its volume swelling by nearly 10%, and the pressure fracturing the surface like a frozen lake cracking underfoot. But there's a problem. Most tectonic fractures elsewhere in the solar system, like Europa's chaotic terrain, form in messy, irregular patterns. The spider's arms, by contrast, align with geometric precision, all converging at a central point like spokes on a wheel. This symmetry suggests something far stranger than simple expansion, perhaps a single catastrophic event, like the abrupt collapse of a vast underground cavity. Enter the wild card, cryovolcanic blowout. Some researchers propose that the spider's center might once have been a colossal ice volcano, its eruptions draining so much subsurface slush that the ground above imploded, leaving behind these radial scars. Spectral data adds fuel to this idea. The fractures show elevated levels of ammonia, a known antifreeze that could keep subsurface fluids mobile long enough for such a collapse. Yet even this explanation falters when faced with the fracture's sheer length. The longest leg stretches over 300 miles, far longer than any known cryovolcanic fissure in the solar system. The most haunting possibility involves Pluto's weird climate cycles. Over millennia, temperature swings could cause nitrogen ice layers beneath the surface to sublimate suddenly, creating voids that trigger Chinese letter collapses. Picture a frozen swamp where pockets of gas burst unexpectedly, leaving the ground above to cave in spiderweb patterns. New Horizons spotted similar, but smaller fractures elsewhere on Pluto, hinting that this might be a global process, with Virgil Fossey representing its most extreme manifestation. What makes the spider truly unsettling is its youth. Unlike Pluto's ancient cratered highlands, the fractures slice through terrain with few impacts, suggesting they formed relatively recently, perhaps within the last 100 million years. Could this mean Pluto's interior is still active, its crust rearranging itself in fits and starts? The answer might lie in the fracture's shadows. Some appear subtly raised at the edges, as if material welled up from below during the cracking process, while others show no vertical displacement at all. This inconsistency implies multiple forces at work: tectonic stretching in some areas, collapse in others, and maybe even pockets of slow, creeping ice flows smoothing the scars over time. For now, the spider remains one of Pluto's most bewildering features, a testament to the violent, dynamic processes shaping even the coldest corners of our solar system. Whether born from shifting ice, erupting slush, or imploding caverns, its presence proves that Pluto's surface is anything but frozen in time. It's a world still writing its own story, one fracture at a time. Pluto's mountain peaks, where crowns of methane snow delicate white caps that dust the highest ridges like powdered sugar on a cosmic dessert. This ethereal frost, captured in stunning detail by New Horizons, presents a baffling atmospheric riddle. On a world where nitrogen dominates the plains and valleys, why does methane preferentially cling to these frigid summits? The answer lies in an intricate dance of temperature, elevation, and chemistry that turns Pluto's thin air into a selective sculptor of icy landscapes. The phenomenon starts with Pluto's peculiar atmospheric layers. Near the surface, temperatures hover around -390 degrees Fahrenheit, cold enough to freeze nitrogen into sprawling glaciers like those in Sputnik Planitia. But methane, with its higher volatility, requires even colder conditions to solidify. As Pluto's scant atmosphere thins at higher altitudes, the temperature drops sharply, creating frost traps atop mountains like the jagged perimeter of Tartarus Dorsa. It's a cosmic inversion of Earth's snow-capped peaks where water vapor freezes at lower elevations, but on Pluto, methane only crystallizes where the air is thinnest and coldest. New Horizons spectral analysis revealed something even stranger. The methane snow isn't pure. It's laced with nitrogen and carbon monoxide, forming a hybrid ice unlike anything seen on other worlds. This suggests that Pluto's atmosphere doesn't separate these gases cleanly. Instead, as air currents carry gaseous methane upward, it mixes with trace amounts of other volatiles before freezing into a delicate crystalline blend. The process is so precise that in some images the snowline appears as sharp as a knife's edge, white peaks abruptly giving way to bare, ruddy slopes just a few hundred meters below. The real enigma is the snow's persistence. Pluto's tenuous atmosphere should make frost formation a fleeting phenomenon, yet these caps endure season after season. One theory points to Pluto's extreme axial tilt, which creates polar-like conditions at high elevations year-round. Another possibility involves hidden reservoirs of methane beneath the surface, venting just enough gas to replenish the snow as it sublimates. Some researchers even speculate that electrostatic forces might help the frost cling to mountain slopes, resisting Pluto's feeble winds. What makes these snowcaps more than just a curiosity is their role as atmospheric barometers. Their distribution and composition record subtle shifts in Pluto's climate over millennia. Darker streaks in the snow, for example, hint at periodic thaws where tholins stained the surface before fresh frost buried them again. The varying thickness of the caps across different mountain ranges may even map ancient wind patterns frozen in time. The implications stretch far beyond Pluto. If methane snow can form and endure in such an extreme environment, what does that mean for similar worlds on the outskirts of other star systems? Could their highest peaks also wear frosty crowns of exotic ices waiting to be discovered? For now, Pluto's shimmering summits remain a testament to nature's ingenuity, a reminder that even in the farthest reaches of the solar system, beauty and mystery go hand in hand. Scattered across Pluto's frozen heart lies one of its most mesmerizing geological puzzles, the polygonal pits of Sputnik Planitia. These aren't random depressions, but a sprawling network of near-perfect geometric shapes, some as wide as cities, their edges so sharply defined they look like tiles in a cosmic mosaic. When New Horizons first revealed these formations, scientists immediately recognized them as evidence of convection, the slow churn of material beneath the surface. But the precision of these patterns defies all expectations. On Earth, convection currents create organic, swirling shapes. Think of boiling oatmeal or lava lamp blobs. Yet here, billions of miles from the Sun, Pluto's icy plains have fractured into polygons so regular they could pass as the work of some celestial architect. The dominant theory involves nitrogen ice behaving like a fluid over geologic time. As heat from Pluto's interior, however faint, rises through Sputnik Planitia's thick ice sheet, it creates circulating cells of sublimation and redeposition. Warmer ice expands upward while cooler material sinks, forming a lattice of rising and falling columns. At the surface, this dance carves out pits where material has drained away, leaving behind raised borders where ice piles up. It's a process similar to the way mud cracks as it dries, or even how the scum on a cooling cup of coffee forms geometric patterns. But there's a glaring inconsistency. Those terrestrial examples are chaotic, while Pluto's polygons are unnervingly uniform, with most spanning between 10 and 30 miles across and displaying crisp, angular boundaries. What could possibly enforce such order? One clue lies in the pit's depth. New Horizons topographic maps show they're remarkably shallow, just a few dozen meters deep, suggesting the convection operates in a thin, fragile layer rather than the deep ice sheet. Some researchers propose that Pluto's nitrogen ice might be layered like a cake, with a stiff upper crust cracking under the stress of movement below. The polygon's regularity could then reflect the brittle nature of this crust, fracturing along mathematically predictable stress lines like a pane of tempered glass. The wild card is composition. Sputnik Planitia's ice isn't pure nitrogen. It's laced with methane, carbon monoxide, and water ice, each with different thermal properties. This cocktail might create just the right conditions for organized fracturing. Imagine stirring honey into molten chocolate. As the mixture cools, it hardens with a different texture than either substance alone. Pluto's ice melange could be behaving similarly, its hybrid structure amplifying small temperature changes into precise fractures, the most tantalizing possibility. These polygons might be ephemeral. Seasonal shifts in sunlight could subtly alter the convection rhythm, causing pits to merge, split, or vanish over centuries. If so, Sputnik Planitia's surface is more like the skin of a bubbling pot than a frozen wasteland constantly rearranging itself in a slow, silent ballet. That would make these geometric scars not just a curiosity, but a living testament to Pluto's hidden restlessness, where even the most rigid formations whisper of motion beneath the ice. Pluto's surface hides a gallery of cryptic art, none more puzzling than the enigmatic X-shaped features carved into its icy canvas. These peculiar markings, scattered across regions like Vega Terra, resemble cosmic graffiti, their crisp lines intersecting at perfect angles as if etched by some unseen hand. Some span several miles, their arms precise enough to rival geometric diagrams, while others appear more weathered, their edges softened by time. When New Horizons first spotted these structures, scientists were left staring at their screens in disbelief. On a world with barely any atmosphere, where erosion should move at a glacial pace, how could such sharply defined shapes persist for millennia? The most striking theory points to wind, but not as we know it. Pluto's whisper-thin atmosphere, 100,000 times less dense than Earth's, shouldn't have the strength to lift dust, let alone sculpt terrain. Yet during seasonal peaks, when nitrogen ice sublimates and temporarily thickens the air, fleeting breezes might stir fine particles. Imagine methane snowflakes lighter than feathers, skimming across the surface like interstellar sandpaper. Over eons, these gusts could sandblast certain areas while leaving others untouched, carving out shallow X's where turbulent winds collide. But there's a flaw. Wind erosion rarely creates such angular patterns. On Mars or Earth, wind-carved features curve and swirl, shaped by fluid dynamics, not rigid geometry. Enter the tectonic hypothesis. Pluto's crust, strained by the gravitational tug of war with Charon and the weight of shifting ice sheets, might fracture in intersecting fault lines. As subsurface ices expand and contract with temperature swings, these cracks could propagate in crisp, X-shaped junctions. Spectral data adds intrigue. Some X's cluster near regions rich in water ice, a material brittle enough to shatter in clean lines when stressed. If true, these markings could be frozen scars from a time when Pluto's interior was far more active, its crust snapping under the strain of a changing orbit or receding ocean. The wild card, cryovolcanic leftovers. If slushy mixtures of water, ammonia, and methane once erupted from Pluto's depths, they might have spread in radial patterns before freezing solid. Picture a frozen fountain, its tendrils meeting at central points to form X's where flows intersected. This could explain why some X's appear raised, their arms standing slightly prouder than the surrounding terrain, like fossilized splash marks from a long-vanished geyser. What deepens the mystery is their uneven distribution. These X's don't pepper Pluto uniformly. They congregate in select zones, avoiding vast stretches of otherwise similar terrain. Does this imply localized forces, hidden heat sources, chemical oddities, or even ancient impact shocks focused in these areas? Or are we witnessing the ghostly imprint of a process that's since gone dormant, its traces preserved only where conditions were just right? The answer might lie in the X's shadows. Some appear fresher, their crisp edges casting sharp lines across the ice, while others blur into their surroundings as if slowly being erased by time. This duality hints that whatever crafted them could still be at work, a slow, silent sculptor reshaping Pluto's face one enigmatic mark at a time. Until another mission visits this frozen frontier, these cosmic signatures remain a riddle, reminding us that even the quietest worlds still murmur secrets to those who know how to look. Pluto's atmosphere is performing a vanishing act right before our eyes, and no one knows if the curtain will ever rise again. This isn't just a slow leak, it's a dramatic collapse, with atmospheric pressure plummeting by over 20% in just 4 years following New Horizons' 2015 flyby. For a world already clinging to a haze 100,000 times thinner than Earth's, such a rapid decline defies all predictions. The culprit seems obvious. Pluto is retreating from the Sun, its elliptical orbit carrying it farther into the Kuiper belt's frozen depths. But the timeline doesn't add up. Seasonal changes on Pluto unfold over centuries, not years. So why is its atmosphere imploding at breakneck speed? The mystery begins with Pluto's volatile ices, primarily nitrogen, with traces of methane and carbon monoxide. For decades, scientists assumed these gases would sublimate steadily as Pluto approached its closest point to the Sun, then gradually refreeze during its long, cold retreat. Instead, the atmosphere peaked around 2015, then started collapsing almost immediately, as if someone flipped a cosmic off switch. Telescope observations in 2019 confirmed the drop, catching researchers off guard. One leading theory suggests Sputnik Planitia, that sprawling nitrogen glacier, might be the key player. As Pluto moves away from the Sun, the heart-shaped plain could be freezing atmospheric gases faster than expected, essentially vacuuming them out of the sky. But calculations show this alone can't account for the staggering speed of the collapse. Enter the wild card, atmospheric chemistry. Pluto's haze layers, those blue-tinted Tholin particles, might be accelerating the freeze-out. These hydrocarbon particles act like microscopic sponges, absorbing gases and clumping together until they grow heavy enough to snow onto the surface. New Horizons spotted this Tholin snowfall in action, but no one predicted how efficiently it could drain the atmosphere once solar heating diminished. Some models now suggest these particles create a feedback loop. As more tholins form, they scavenge more gas, which leads to even more Tholin production, a runaway process that could strip Pluto's sky bare in decades rather than centuries. The stakes go beyond Pluto. If such a tenuous atmosphere can collapse this abruptly, what does that mean for other distant worlds? Could Eris or Makemake experience similar atmospheric death spirals? Even more tantalizing is the question of reversibility. Is this a permanent farewell, or could Pluto's atmosphere rebound? On Earth, ice ages come and go, but Pluto's cycles operate on a grander scale. Its next summer won't arrive until the 23rd century. By then, the nitrogen now freezing onto its surface might remain locked away forever, or it could reignite the atmospheric engine, turning Pluto back into the hazy enigma we glimpsed in 2015. For now, every telescope trained on Pluto watches for clues. Will the collapse continue linearly, or is there a flaw, some minimal atmospheric state where equilibrium takes over? And what of the iconic haze layers? If they vanish entirely, Pluto's striking blue halo could fade into memory, leaving behind a stark, airless world. Yet there's a poetic irony in this cosmic drama. The same volatility that makes Pluto's atmosphere so fragile also makes it one of the solar system's most dynamic, a reminder that even at the edge of darkness, change is the only constant. Whether this is a temporary hiccup or a final curtain call remains one of the dwarf planet's most urgent mysteries, unfolding in real time across 4 billion miles of space. Pluto's moons spin through space surrounded by a puzzle that defies cosmic logic. Where is all the dust? In nearly every other moon system, from Saturn's glittering rings to Mars's cratered satellites, constant micrometeorite impacts kick up clouds of fine debris, coating surfaces and filling orbital pathways. But Pluto's 5 moons, Charon, Styx, Nix, Kerberos, and Hydra, float in eerily clean orbits, their surfaces suspiciously free of the dusty blankets that should have accumulated over billions of years. Even Charon, Pluto's largest companion, shows only a smattering of impact craters, none of the fine-grained powder that typically settles like snow across airless worlds. This glaring absence isn't just odd, it's a violation of the solar system's most basic rules of celestial wear and tear. One explanation points to Pluto's chaotic gravitational environment. The dwarf planet and Charon orbit a shared center of mass, creating a gravitational tug of war that stretches and squeezes the space around them. Any dust particles drifting into this zone could be flung outward like pebbles from a slingshot or dragged down to the surfaces by complex tidal forces. But there's a catch. This doesn't account for the moon's own ability to generate dust. Micrometeorites should still pelt their surfaces, chipping off fragments that would linger in orbit. Yet New Horizons saw no hint of dusty halos, no faint rings clinging to these worlds. Enter electrostatic forces, an invisible hand that might be scrubbing Pluto's system clean. In the vacuum of space, UV radiation from the distant sun can charge dust particles, giving them a slight electric field. On larger worlds like Earth's moon, gravity easily overpowers this effect, pulling dust back to the surface. But Pluto's moons are tiny, with gravity so weak that even a whisper of electrostatic repulsion could be enough to launch dust grains into space forever. Picture a world where every impact sends a spray of particles skyward, only instead of drifting back down, they're repelled by the surface's own charged terrain, ejected into the void like breadcrumbs tossed into a cosmic wind. Another possibility, the moons themselves might be unusually fluffy. Spectral data suggests their surfaces are packed with porous, fragile ice, more like compacted snowballs than solid rock. When micrometeorites strike, they could burrow into this soft material without kicking up the usual debris, like a bullet fired into a snowbank. Over time, this might leave the moons nearly dust-free, their surfaces constantly healing like a self-erasing chalkboard. But the most tantalizing clue lies in Pluto's extended family. Other Kuiper belt objects like Haumea and its moons also show surprisingly dust-free environments. This hints at a broader pattern, a hidden rule governing small, icy worlds at the solar system's edge. Could their distance from the sun, combined with unique ice chemistry, create conditions where dust simply can't persist? Or is there some unseen process, solar wind interactions, seasonal outgassing, even magnetic anomalies scouring these systems clean? For now, Pluto's pristinely kept moons remain a cosmic housekeeping mystery. Their spotless surfaces challenge our understanding of how small worlds evolve, proving that even in the realm of dust and debris, the universe still has a few surprises up its sleeve. Pluto's highlands wear an armor of dragon scales, vast swaths of overlapping, ridged terrain that ripple across the landscape like the hide of some mythical beast. These mesmerizing formations, scattered across regions like Vega Terra and Tartarus Dorsa, form intricate patterns that seem almost too deliberate for a world so distant and frozen. Each scale-like plate spans miles in width, their raised edges casting sharp shadows that create a visual texture unlike anything else in the solar system. When New Horizons first beamed back these images, scientists scrambled to explain how such precise, reptilian textures could emerge on a world where sunlight is 1,000 times weaker than Earth's, and the average temperature hovers near absolute zero. The most plausible explanation ties these scales to Pluto's extreme climate cycles. Over millennia, the dwarf planet's wild axial tilt, a staggering 120 degrees, creates seasons so lopsided that entire hemispheres alternate between decades of weak sunlight and centuries of uninterrupted darkness. During these long, frigid winters, volatile ices like methane and nitrogen freeze out of the atmosphere, blanketing the highlands in thin frost. When sunlight eventually returns, the ices sublimate unevenly, leaving behind tougher water ice in raised ridges. Repeat this cycle over millions of years, and you get layers of material slowly carved into these overlapping plates, like tree rings recording Pluto's climatic mood swings. But here's where the mystery deepens. While sublimation can create textured terrain, think of the Swiss cheese landscapes of Mars's polar caps. Pluto's dragon scales are far more organized. Their edges align in near-perfect arcs, as if guided by some unseen force. One theory suggests that Pluto's weak gravity allows frost to creep sideways as it sublimates, creating these sinuous patterns. Another idea points to thermal contraction. As the surface cools and cracks, fractures propagate in curved waves, similar to how mud forms polygonal cracks as it dries. Yet neither explanation fully accounts for the scales' uniformity or their sheer size. Some individual plates stretch over 20 miles across, dwarfing any similar features found on other icy worlds. The wild card, wind. Despite Pluto's atmosphere being thinner than a laboratory vacuum, subtle breezes might still play a role. During periods of heightened sublimation, escaping gases could generate just enough airflow to redistribute fine ice particles, sculpting the scale's edges over eons. New Horizons detected faint streaks near some ridges that look suspiciously like wind-blown deposits, hinting that even whispers of wind can shape Pluto's geology when given enough time. What makes these formations truly enigmatic is their patchy distribution. They dominate certain highland regions while vanishing entirely in others, as if some invisible boundary dictates where they can form. Spectral data adds another layer of intrigue. The scales often appear richer in methane ice than their surroundings, suggesting localized chemistry might be at work. Could underground reservoirs of methane be seeping up through fractures, creating a feedback loop where certain areas are primed for scale formation? Or does Pluto's interaction with Charon's gravity flex the crust in just the right way to encourage these patterns? The dragon scales aren't just a geological oddity, they're a record of Pluto's hidden restlessness. Their crisp edges and lack of overlying craters suggest they're relatively young, possibly reshaped by recent climate cycles. If so, they're proof that even at the solar system's edge, where time seems frozen, Pluto's surface is still being rewritten, one scale at a time. Whether carved by frost, fractured by cold, or brushed by ethereal winds, these formations remind us that beauty and mystery often wear the same armor, especially on worlds that refuse to be easily understood. Pluto's geological hyperactivity has scientists scratching their heads. How does a tiny, frozen world at the solar system's edge power cryovolcanoes, shifting glaciers, and a hazy atmosphere? The leading suspect, radioactive decay deep in Pluto's rocky heart. While most Kuiper belt objects sit frozen in time, Pluto's core might still be cooking, its heavy elements like uranium and potassium slowly breaking down and releasing heat over billions of years. This steady simmer could explain why Pluto's surface refuses to stay static, even as neighbors like Eris and Makemake show no signs of similar drama. But here's the catch: Pluto isn't large enough for conventional models to predict this much residual warmth. Earth's radioactive core stays toasty because our planet is massive, its thick mantle insulating the heat like a cosmic blanket. Pluto, by contrast, is barely larger than some asteroids, with a core that should have cooled into dormancy eons ago. Yet New Horizons spotted telltale signs of ongoing activity. Young terrain with barely any craters, tectonic fractures spiderwebbing across the surface, and possible cryovolcanoes oozing slushy ice. If radioactivity is the engine behind this, Pluto's core must be unusually rich in heat-producing elements, perhaps a relic from the violent collisions that shaped the early solar system. Compare this to Eris, Pluto's near twin in size and composition. Despite their similarities, Eris shows none of the same geological flair. Its surface is heavily cratered, its terrain ancient and undisturbed. This sharp dichotomy raises a tantalizing question. Did Pluto get extra helpings of radioactive isotopes during its formation, or is something else amplifying its internal warmth? One theory suggests Pluto's chaotic axial tilt, tipped over like a spinning top knocked off balance, creates tidal friction with its moon Charon, flexing its interior like a stress ball. Another possibility involves exotic antifreeze compounds like ammonia mixing with subsurface water, lowering the melting point of ices and keeping pockets of slushy brine liquid far longer than expected. The implications stretch beyond Pluto. If radioactive decay can power geological activity in such a small, cold world, what does that mean for other distant objects? Could Sedna or Kuiper, much farther out in the Kuiper belt, also hide warm cores beneath their icy shells? Or is Pluto a cosmic outlier, its unusual birth granting it a slow-burning furnace that others lack? For now, the dwarf planet's radioactive heartbeat remains one of its most profound mysteries, a reminder that even in the coldest corners of space, heat lingers in unexpected ways, defying our models and reshaping our understanding of what tiny worlds can do. The real puzzle isn't just Pluto's warmth, but its selective warmth. Why do some regions, like Sputnik Planitia, show signs of constant renewal, while others, like the dark highlands of Kuiper Macula, appear frozen in time? If radioactive decay were evenly distributed, shouldn't the entire surface simmer equally? This unevenness hints at a more complex story. Perhaps heat is channeled through specific pathways, like ancient fractures or underground aquifers, creating localized hotspots where geology stays lively. Or maybe Pluto's core isn't uniform, with pockets of concentrated radioactive material acting like buried furnaces beneath certain regions. The contrast with other Kuiper belt objects becomes even starker when you consider their surfaces. Make's bright, methane-coated plains show no evidence of cryovolcanism or tectonics, while Haumea's elongated shape suggests it froze solid early in its history. Pluto, meanwhile, refuses to play by the rules. Its radioactive heart might not just be a relic of its formation. It could be a ticking clock counting down toward some future transformation. As the isotopes decay, their heat output dwindles. Is Pluto's current activity a last gasp of warmth before it settles into the same icy slumber as its neighbors, or are there other forces at work, stretching its geological lifespan even further? Until another mission ventures to this distant world, the question remains open. Pluto's radioactive engine, whether solitary or part of a broader cosmic pattern, challenges our assumptions about how small worlds evolve. It's a reminder that even in the silent reaches of the solar system, beneath layers of ice and time, the fires of creation still flicker. Pluto's largest moon, Charon, holds a secret on its frozen face, a sinister stain stretching across its northern pole like spilled ink. Nicknamed Mordor Macula after the shadowed realm from Lord of the Rings, this rusty blotch stands in stark contrast to Charon's otherwise pale water ice crust. But unlike Tolkien's fictional wasteland, this isn't the work of dark magic. It's a real-world enigma that challenges our understanding of how celestial neighbors interact. The leading theory, Pluto's hazy atmosphere might be slowly painting its moon red, one molecule at a time. The process begins with Pluto's nitrogen-rich sky, where sunlight breaks methane molecules apart, transforming them into complex hydrocarbons called tholins. These sticky, organic compounds give Pluto its reddish hues, but they don't stay put. Over millennia, some tholins escape Pluto's weak gravity, drifting into space like cosmic graffiti. Charon, locked in its tight orbital dance just 12,000 miles away, becomes the prime target for this slow-motion spray paint. The moon's polar regions, with their extreme cold and long winters, act like flypaper for these wandering molecules, capturing and preserving them in a permanent stain. Yet this explanation isn't as tidy as it seems. For one, Charon's stain isn't uniform, it's splotchy, concentrated in the north with odd streaks trailing toward the equator. If Tholin fallout were the sole culprit, the entire pole should be evenly tinted. New Horizons spotted another anomaly. Mordor Macula sits directly under the path of Pluto's escaping atmosphere, but the stain's edges don't perfectly align with theoretical deposition models. Some patches appear darker and fresher, while others look faded, as if Charon's surface is actively resisting or erasing the pigment in certain spots. The plot thickens when you consider Charon's seasons. Unlike Earth's moon, Charon's poles take turns facing Pluto for decades at a time due to its extreme axial tilt. During these long winters, temperatures at the inactive pole plummet so low that even methane freezes solid. This deep chill could create temporary cold traps, sucking tholins from Pluto's atmospheric exhaust like a vacuum. But here's the catch: Mordor Macula isn't symmetric. The South Pole, though equally frigid, shows only faint discoloration. This lopsidedness hints at something stranger. Perhaps Charon's own geology is influencing the stain's spread. One compelling theory suggests that cryovolcanic activity might be scrubbing the southern pole clean. Charon's surface bears fractures and smooth plains that hint at ancient ice eruptions, which could have resurged areas and buried older tholin deposits. Meanwhile, the northern terrain appears older and more stable, allowing the stain to accumulate uninterrupted. Alternatively, electrostatic forces powered by solar wind might be levitating tholin particles off certain regions, leaving bizarre, patchy distributions. The most haunting possibility: Charon's stain might not be purely external. Spectral data reveals traces of ammonia and carbon-rich compounds within Mordor Macula, materials that could originate from Charon's own interior, seeping up through cracks and reacting with Pluto's tholin rain. This would make the stain a hybrid, a cosmic collaboration between two worlds. If true, it's a reminder that even in the solitude of the Kuiper belt, no world is truly isolated, their fates intertwined by gravity, chemistry, and time. For now, Mordor Macula remains a cryptic testament to the dynamic relationship between Pluto and Charon. Whether painted by atmospheric leakage, shaped by hidden geology, or born of some deeper synergy, this dark polar blemish is more than a curiosity. It's a window into the invisible bonds that tether moon to planet and the subtle ways celestial bodies leave their mark on one another. As the only known example of such staining in our solar system, it stands alone, a rogue brushstroke on the canvas of the cosmos, challenging us to decode its origins. Pluto has taken us on a journey through 25 of the most bewildering cosmic riddles, from its drifting glacial mountains and tectonic spiderwebs to its vanishing atmosphere and crimson-stained poles. Each mystery peels back another layer of this tiny world's defiance, proving that size means nothing when it comes to planetary intrigue. Think about it: a dwarf planet with floating hills that glide like ships on a frozen sea, a moon system so chaotic it defies orbital physics, and cryovolcanoes that might still ooze icy sludge despite being billions of miles from the sun's warmth. These aren't just quirks, they're revolutionary clues that challenge everything we thought we knew about cold, distant worlds. What makes Pluto's enigmas so thrilling isn't just their strangeness, it's what they reveal about the universe's creativity. For centuries, we assumed the outer solar system was a silent graveyard of frozen relics, but Pluto laughs in the face of that assumption. Its heartbeat persists through radioactive decay we can't fully explain. Its atmosphere collapses and rebounds like a cosmic lung, and its surface renews itself in ways that put active planets to shame. This isn't just a frozen rock. It's a dynamic world with a personality, one that whispers tantalizing hints about hidden oceans, exotic chemistries, and forces we haven't even named yet. The best part: we've barely scratched the surface. New Horizons' 2015 flyby was a fleeting glimpse, a single snapshot in Pluto's 248-year orbit. Imagine what we discover with an orbiter lingering for years or a lander touching down on those nitrogen glaciers. Future missions could uncover whether Sputnik Planitia truly hides a subsurface sea, if Right Mons still rumbles with cryovolcanic murmurs, or why Charon's polar stain refuses to spread evenly. Every unanswered question is an invitation not just for scientists, but for anyone who's ever looked at the night sky and wondered what else is out there defying expectations. So here's to Pluto, the underdog of the solar system, a world that lost its planetary title but gained something far more captivating, the crown of mystery. As we wait for the next chapter in its exploration, one thing's certain: the universe always keeps its most fascinating secrets in the last places we think to look. Now it's your turn. Which of Pluto's puzzles leaves you most awestruck? The drifting hills, the bleeding poles, the atmosphere that vanishes like a magic trick? Drop your thoughts below and keep looking up. The next big cosmic revelation might be lurking in the Kuiper belt, just waiting for us to connect the dots.